Hi everyone. So in this lecture, I thought I'll talk a little bit more about CMRR of the instrumentation amplifiers. So if you guys recall from the previous lectures, we said that the CMRR of a instrumentation amplifier depends upon how well these resistors are matched, mainly the resistors of the second stage. We derived an expression for the CMRR and we showed that the CMRR of the instrumentation amplifier is mainly dominated by the matching, how well the second stage resistors are matched. R4 and R4 should be matched and R3 and R3 should be matched. And therefore we said this is one of the main reasons why these resistors R3, R4, they are all they all mostly come as integrated resistors, meaning they will all come within a single chip. They will not be external. And also the reason is that since the second stage is acting as a subtractor, which is the second stage is acting as a differential to single inlet converter, it needs to have better matching, and you cannot add programmability in the gain in the second stage. Okay, again we said that leads to, if I add programmability in the second stage, that can lead to poor CMRR. So we said all the programmability is usually added in the first stage itself. Okay, so just keep this in mind, the programmability point. We will later talk about bandwidth of amplifiers, and this is very helpful there. So now I'll come back to this discussion. So we said CMRR is mainly determined by the second stage. But are there any other sources of CMRR other than this resistor mismatches? And that turns out to be, yes, that turns out to be true. There are other sources as well, and that happens to be the opamps in the first stage. Right? If the two opamps are identical, we said that even the resistor mismatches don't matter. Even the first stage resistor, this RF and RF can be mismatched. It won't really impact my common mode error. Okay, but if the opamps themselves have a gain mismatch, if the gains are not exactly equal, then we have a problem. Now, how do I analyze the impact of opamp gain on the CMRR performance? So for that, if you guys think about it, if you apply a common mode input, the output also comes to VCM, right? Assume if the opamp is ideal, this node comes to VCM, this node comes to VCM, and this node comes to VCM. Right? So if this node is at VCM, no current flows through the resistor, and therefore the output nodes will also be at VCM. So as far as common mode is concerned, this opamp, both these opamps, A1 and A2, I've called them A1 and A2 here, they act like voltage buffers. Now we know for a voltage buffer, which is something I have shown here. So if you look at the voltage buffer, an ideal an voltage buffer with a finite opamp gain A, the output voltage is not exactly equal to input voltage. In fact, it is given by A by 1 plus A times the input voltage. I can write this as 1 minus 1 by 1 plus A times Vi. So it can be written as Vi into 1 minus 1 by A. Okay, again, since A is generally much greater than 1, I can do this approximation, which means the output voltage is equal to the input voltage minus a small factor. So this will be like your error factor. Vi minus of Vi by A will be your error factor. Okay, it will not exactly be equal to input voltage. It will be slightly lower than that. So we will use this result to do the analysis here. So all I need to do, previously in my analysis, I was assuming these two nodes, the inverting terminals were exactly equal to VCM. Now, because I'm using this fact that as far as common mode signals are concerned, the first stage is going to act like two buffers. So I can use this analysis. The non-inverting terminal will not be exactly equal to VCM, but instead it will be equal to VCM into 1 minus 1 by A1 or A2. So this node here will be equal to VCM into 1 by 1 minus A2, and this node here will be equal to VCM into, this node here will be equal to VCM into 1 minus 1 by A1. So now from this I can compute, I'm going to assume that the second stage is ideal. The second stage is ideal. What is the second stage going to do? It's going to just amplify the difference. The output of the second stage will simply be equal to VO2 minus VO1. So VO2 is this node voltage and the VO1 is this node voltage minus VO1 times R4 by R3. If you look at this circuit, what exactly is VO2 minus VO1? VO2 minus VO1 is nothing but the potential drop across the three resistors. So you have three resistors like this. You have RF, R and another RF. Okay. So this node voltage is VO1 and this node voltage is VO2. So VO2 minus VO1 is the potential difference between this. Okay, so that's VO2 minus VO1. That is simply the voltage drop across RF plus the voltage drop across R plus the voltage drop across the RF in the upper arm. Now how do I find that? All I need to do is find the voltage drop across R. Because the currents are all equal, I can use that, to compute the other voltages as well. So this node voltage across the resistor, this, if I'm just plotting showing the resistor alone here, this is this node voltage here. This node voltage will be at VCM into 1 minus 1 by A2. And the node above of the other node of the resistor will be equal to VCM into 1 minus 1 by A1. Now the current that's going to flow, I'm computing this current in this direction, is simply given by VCM. You subtract these two voltages, it will be VCM into 1 by A1 minus 1 by A2, okay, divided by R. That's the current. The voltage across the resistor, the voltage across this resistor is simply given by this, VCM into 1 by A1 minus 1 by A2. And the voltage across the two resistors, I'll simply, because they both are going to be same, the resistor values are same, so the voltage drop will also be same. I'll call it as 2 into this voltage divided by R, that's the current, VCM divided by R into 1 by A1 minus 1 by A2 times RF. So I'll take this factor RF out, so it will be VCM by R. So now I'll just erase all of this. We have written the expression for the voltage VO2 minus VO1. So once you know VO2 minus VO1, V0 is very easy. We can easily compute V0. So VO2 minus VO1, previously it was 0 for common mode inputs. Now I am showing that in the presence of finite mismatch between the opamp gains, the opamp's DC gains are not same, then you will have this result. So it will be 1 plus 2 RF by R, which is the differential gain of this stage, times VCM into 1 by A1 minus 1 by A2. That's your VO2 minus VO1. And if I compute V0, so I'll have to multiply this term with R, so that will be R4 by R3 times 1 plus 2 RF by R times, so I'll write it this way, I'll write it as A2 minus A1 by A1 A2, okay, times VCM. This happens to be your output voltage in the presence of common mode signal. So this term is nothing but your differential gain. This is your differential gain, AD. Okay, and the common mode gain is ACM. So V0 by VI, VCM is your common. If I take VCM to the denominator, I get the common mode gain. Okay, so that will become your, so I'll write it as, I'll take VCM out. So V0 by VCM is simply equal to ACM. This here is AD. So AD by ACM, so that will be AD by ACM will be equal to, that's your CMRR in linear units, will simply be equal to 1 divided by A1 minus A2 into A1 A2. Okay, so now from this your CMRR is, I can simply take 20 log off and I get this expression. So your CMRR is given by minus 20, minus I've written because I've just inverted this. So I can write it as minus 20 log off. So I'll remove VCM here. So it will be delta A upon A1 A2. Okay. So I've taken mod here. A delta A here is simply equal to A2 minus A1. Delta A here equals A2 minus A1. I'm just taking mod here because when I take log, you should always, the quantity should always be positive. So that's what I'm taking mod here. So mod A divided by A1 into A2. That's the CMRR of your amplifier, CMRR of your instrumentation amplifier. Okay, so just to mention one point, I assumed that the second stage amplifier doesn't really come into the picture. That's because the second stage A3, the gain A3 doesn't impact the common mode gain. If you find the gain, overall gain, it will only impact the differential gain. So if you apply, we will later show that as well, identical inputs at the two terminals, right, at the two subtractor input terminals, the output will be 0. Even if you assume the op-amp's gain is finite, you can easily show that the output will be 0. What it does, this gain, it will slightly distort the differential gain. It will slightly change the value of the differential gain. So that will appear as a gain error. We'll talk about that later, but that shouldn't impact my CMRR performance. So that's why I ignored that. I'm only considering this part. So now if you look at it, I've gotten an expression for CMRR in terms of the error between the two gains. Now let's assume, why am I assuming that the two gains will have errors? Because see, these amplifiers are built using BJTs and MOS circuits. Again, these BJTs and MOS circuits, the DC gains will be dependent on what? GMs, R naughts of those transistors. These are all process dependent numbers, and they are also prone to mismatches. No two devices, no two amplifiers will be exactly identical. They will have some mismatches. So that's why I'm assuming mismatches exist. So let's for the time being assume that the gains are 10% mismatched. There is a mismatch of 10%. So let A be the gain of the first op-amp. The gain of the second op-amp, I can assume it to be 1.1 times A. So the gain error, here is the error in gain is 10% error. It can be even lower. Okay, these are all analog ICs. They are specially designed analog ICs. So you can expect them to have lower gain errors. But if you have CMOS ICs, let's say you are building this whole instrumentation amplifier kind of an architecture that goes into a CMOS chip. Okay, a chip that uses CMOS devices which are meant for digital design, meant for, let's say, DSP processors or microprocessors or microcontrollers. So there, if you are going to build an analog circuit in a mixed signal chip, you will normally be using devices that the digital guys will be using. So those devices can have higher mismatches. Okay, they are not normally optimized for analog performance, so they tend to be poorer in performance. Okay, so that's why I've assumed some mismatch. They will have higher mismatches. So here I've taken a 10% mismatch. Then the gain is given by 0.1 by A. The CMRR is given by 20 log of 0.1 by A. So now if I need a gain of, let's say, 140 CMRR of, let's say I need a CMRR of 140 decibels, then what should be the amplifier's gain, assuming a 10% mismatch in the gains of the two amplifiers? From that you can easily calculate, equate this to this, minus 20 log of 0.1 by A. In the gain in op-amp's gain in decibels comes out to be 120 decibels or 10 power 6 volts per volt. Okay, so you can easily do this. I'm just finally quoting the result here. This is a very simple calculation. So op-amp's gain will be equal to 120 decibels. So if I want to achieve very high CMRR in the order of 140 decibels, the individual op-amps that are used in this instrumentation amplifier, they also need to have very high gains. Okay, only then you can achieve very high CMRR. When you want to achieve high CMRR, let's say you have matched all your resistors very accurately. Even then, you may end up having some finite CMRR because the op-amp gains are not matched. So then you will have to ensure that for the op-amps to have good matching, the DC gain itself can be higher. Okay, so here I'm assuming that the gain, DC gain, and the percentage error are not correlated, meaning I can have a fixed percentage error for higher gains as well. Okay, which is not a bad assumption. Yeah, so that's something to keep in mind. So now I have derived an expression for the op-amp's gain based on CMRR. So this is how it gets decided. If you are a circuit designer who is designing these op-amps that goes into an instrumentation amplifier, you'll have to keep all these points in mind. Finally, when we talk about gain errors, the other most important thing is the differential gain error. See, the differential gain is given by 1 plus 2 RF by R times R4 by R3. R4 and R3 are the second stage resistors. So in some applications, you may want your gain to be extremely accurate. You can't tolerate errors in gains itself. I mean, let's say this gain is 1000, you may want this gain to be as accurate as close to 1000 as possible. Those are called precision amplifiers. You want the gain to be very precise. If you recall, that is how we began talking about feedback and all that, right? So we said gain errors can lead to saturating or noise amplification in cascaded amplifiers. Okay, when we talk about when we were talking about the telephone amplifiers, right? So that's one big problem. So let's say we want very high gain accuracy, then what determines the accuracy of gains? So like in any op-amp based circuit, the gain accuracy will be mainly determined by the op-amp's DC gains. So let's start with a simpler circuit, which is your subtractor. So if you want to find, let's find the common mode gain of the subtractor and the differential mode, or I'll just derive an expression for the subtractor in terms of VO1 and VO2. Assume the op-amp's gain is finite. Okay, you can easily apply principle of superposition and easily show that the overall gain of the op-amp will be given by VO2 minus VO1. It acts like a subtractor into RF by R3. This is your ideal subtractor gain, multiplied by 1 plus A3 beta. Here your beta is given by R3 by R4 plus R3. Okay, so that's your beta, and this can also be written as 1 plus R4 by R3. Okay, so this can also be written in this format. So 1 upon the gain, approximately the gain of the subtractor. So if let G2 denote the gain of the subtractor, which is given by R4 by R3, then beta can be written as 1 plus G2. Okay, so higher the gain, the lower will be the feedback factor. So what is shown here, your V0 depends upon the gain. The gain error is, ideally you want the gain to be R4 by R3, but the error factor is given by this. So you can express this as 1 minus, I can use this approximation. 1 plus x is approximately 1 minus x. I'll use that approximation for small values of x, which will hold true here, which will be 1 minus 1 by A3 beta. So now you can look at this result itself directly here. Even if you assume the op-amp has a finite gain, the common mode error is 0. I mean, if you assume VO1 and VO2, or if you apply some common mode inputs to both these inputs, common mode signals to both these inputs, the output will be 0, even if you have a finite op-amp's gain. Okay, so that's why we didn't include this in the CMRR computation. So next step, we'll compute the gain of, the gain of okay, so we'll compute the gain of the differential amplifier stage. Okay, so this is this is the one. Yeah, so to compute the gain of the first stage in terms of the op-amp's gain, so here, since we are interested in calculating the differential gain, right, so we can assume that we can use the differential half circuit for the first stage and compute the gain of the differential half circuit directly. Since we are mostly talking about differential signals here, I'll assume for the time being, in this analysis, which is a very fair assumption, that these two op-amps are almost the same. Right? Our goal is right now not to identify or analyze mismatches. Our goal is now just to find the DC gain. What does it depend upon? The differential gain of the instrumentation amplifiers. Okay? How does it depend upon the op-amp gains? So shown here is a half circuit. We can directly find the gain of this half circuit. This is again a non-inverting amplifier. We have already done this. See, recall, use this result 1 by beta times 1 plus 1 by A beta. This is the gain of a negatively fedback amplifier. You can use this result and arrive at this. Okay, so I'm not going through that because we have already done that in the previous lectures. So I'm quoting the final result. So 1 by beta is the gain of the first stage, which is 1 plus 2 RF by R. That's the gain of the first stage, multiplied by 1 by 1 plus 1 by A beta 1. A is the op-amp's gain. Okay, so if the gain, let G1 denote the gain of the first stage. Okay, if G1 denotes the first stage's gain, that's given by 1 plus 2 RF by R, I can express beta, the feedback factor of the first stage, to be, the feedback factor of the first stage is beta 1 is R by 2 upon R by 2 plus RF. This can be written as 1 by 1 plus 2 RF by R, which is nothing but 1 by G1. Okay, it's beta 1 is given by 1 by G1. So now we have this final result. The gain of this amplifier we have expressed in terms of the op-amp gains. I can now compute. See, this is so this is VO2 minus VO1. We can again find the differential gain of the first stage is given by this, multiplied by the differential gain of the second stage, which is a differential to single-ended converter. Gain of the second stage, you get the overall gain. So I have written the overall gain here. So these are these two terms because of the op-amp's finite DC gains. You can rearrange the terms here. I can use this approximation. 1 by 1 plus x is approximately equal to 1 minus x. From that, you will get an expression like this. So your output voltage will simply be equal to the ideal differential gain, which is R4 by R3 into 1 plus 2 RF by R times this term. So the error in gain, this term here becomes the gain error here. Okay, so how do we define gain error? Delta AD, error in gain divided by AD. So you subtract AD out of this and divide it by AD, you will get this expression. So if you need a gain error, let's say in the order of 10 ppm, usually it's mentioned in the orders of 10 parts per million, which is nothing but 10 power minus 5. Okay, 10 into 10 power minus 6, which is 10 power minus 5. That will decide what should be your values of A1 and A3. Okay, so I'll use this fact. Beta 1 is the feedback factor for the first stage, which is given by 1 by G1. And beta is the feedback factor for the second stage, which is given by 1 by 1 plus G2. That's the second stage gain. So using that, I can write this gain error as this term as 1 by A1 beta, which is G1 upon A1 plus the second stage will be 1 plus G2 upon A3 times 100. Okay, this will be your, I'll have taken mod of this, will be your gain error. Okay, so if you look at this expression, right, it depends upon the gain of the amplifier and also the DC gain, the gain of the closed loop amplifier and the DC gain of the op-amp. So here I want to just mention one point about instrumentation amplifiers. Usually when we see most of the commercial instrumentation amplifiers, we will try to get the maximum gain out of the first stage. So generally G1 will be much greater than G2. The overall gain will be equal to G1 times G2. I mean, which is simply 1 plus 2 RF by R times R4 by R3. So this we are calling it as G2 and this we are calling it as G1. Most of the gain, see, we saw the first stage gain is normally made programmable, and that gain mostly comes from the first stage itself. A big chunk of the gain. So you can actually probably let me show you guys, So if you guys look at this design, this is one of the previous chips that we were looking at. The first stage gain is close to, this is a fixed gain differential amplifier with a gain of 2000. Okay, the first stage gain is 200 and the second stage gain is 10, almost 20 times smaller. The second stage gain is almost 20 times smaller compared to the first stage. And if you guys look at the other one, the second stage gain is just unity, it's just 1. Almost all the gain, 1 to, it's a programmable gain amplifier with most of its gain comes from, in fact all of its gain comes from the first stage. So that's what I said. Most of the gain is generally achieved by varying the gain of the first stage. Okay, so we are back to this result here. So using that, I can argue that this will approximately be equal to G1 by A1, where G1 is generally much greater than G2. So I'm going to use that result and say that, if assume A1 and A3 are in similar orders, okay, so then the gain error reduces to G1 by A1. So now if I need a gain of 10 power minus 5 gain error, so that will tell you A1 should be equal to uh, G1 upon G1 times 10 power 5. So the first stage gain multiplied by 10 power 5 should be your A1. This is assuming you need a 10 ppm error, which is a very, very high and a very precise gain number, okay. If you have lower, if you, let's say you need 10 power minus 3 gain errors, 1%, 0.1% gain error, you want, let's say, gain error of 0.1%, that's just 10 power minus 3, it will be 1000 times G1. So if your first stage gain is 100, this should be at least 10 power 5, okay, or 100 decibels. So that's how you arrive at the gain specifications from a gain error point of view. Few moments back, we derived the gain specification for the first stage amplifier from a CMRR point of view, okay. So all we are seeing in these analysis is that the first stage is the most critical one as far as CMRR is concerned, or even differential gain error is concerned. This first stage is the more crucial one, because that guy gives you the maximum, most of the gain, right? So when you're budgeting the gain of this differential instrumentation amplifier, most of the gain comes from the first stage. So that's it about the gain errors for instrumentation amplifiers. In the next lecture, we'll talk about the frequency response of instrumentation amplifiers.